Let's start here. Why did I want to make this design? Because I wanted to control a shaft through a thin steel wall. And why would I want that? Well, I can show you. If you look at these lamps, you'll see a thin steel wall and a pin, and the designers took control of the pin in the steel wall. Now you have an adjustable lamp. If you look at this lamp, you'll see the same. A thin steel wall and a pin taking control of a joint. If you look at this fan, it's a thin steel wall and a pin, and the designers took control to form a dually supported joint. And the same is true here. We have a hole in a thin steel wall that gives us another degree of freedom. And then if you look back further, we have still a pin in a thin steel wall that carries a load and takes control. If we come over to this television and look at the mount, we have a 4-bar linkage, and we have a pin in a thin steel wall that supports it. And then this beam is just made up of 2 more thin steel walls that are constrained also by the pin. And all throughout this design, it's the same. If we look at this dishwasher, we have a smooth operation and a supported hinge on this door that's based on a pin going through a thin steel wall here. If you're relaxing on the couch, you're supported by several pins in thin steel walls. And the friction and the movement and the freedom to move is all controlled by the materials and the decisions around that pin in those thin steel walls. If you take apart a monitor mount, an adjustable mount, then you will find these beams that are made up from a pin in a thin steel wall for all of the joints. These are just covered in plastic. In fact, you'll notice the whole world revolves around a pin that goes through a thin steel wall. So I produced this sleeve and its variations to begin to have for ourselves a set of answers that take control of pins going through steel walls. This apparatus here gives us a gearbox, but the more important thing is to have a really nice set of offerings that give us that control and give us the ability to adjust the design to manipulate that joint right there. You may be getting new ideas on how to plan a design for multiple assemblies and what assemblies are possible to be built with 3D printed parts. So this is another integrated part with off-the-shelf parts, and so I'm using keyword Printegrate for the online posts that have parts like this. And as a designer, even if you're not a mechanical engineer, you should gain some insights as to how do you approach the specific problems. What problems do we encounter when we're trying to create something from scratch to do a job? And how does a mechanical engineer think through a design process and make steps out of it? I should also mention that we're still on track. From 6 months or a year back, I showed people how to throw together this simple joint bracket that holds a big fan, that allows you to position it, that is simply made from the same components we're going to look at today. And the next steps are to be able to take more control over those joints to control the friction or the clicking. And that means we're going to need some sort of components that give us access to manipulate the joint. And that's where we're going. So I want this bolt to go securely into these holes. Let's just consider one hole. How do I get the bolt to fit? Well, I'm going to use a reducer. So I'll reduce that size from large to small, 8 millimeters. How will such a reducer install into this wall? It's going to have a slip fit. It's going to just pass in without pressing. And so that answer of the slip fit is defined in this diameter here. exactly where you'll see the flush wall of my steel on the flush surface located right here. How will I prevent the sleeve from passing all the way through and have it just contact and stop here where I want it? Well, that's going to be defined by having a diameter larger. Instead of a slip fit, we're just saying, depending on this diameter, we need a millimeter or two larger than this 22 millimeters. And so that answer is embedded in this diameter right here. Okay, so we have something thin that slips in. Conceptually, we said, how will the bolt fit into this reducing device? Well, it's going to also have a slip fit. And so that hole is defined by the diameter of the screw plus some amount that gives me the clearance fit. And that answer actually is a routine answer, and that lives in a set of design rules. I actually published a PDF, 18 pages so far, and that's available, although it's just a draft. Okay, so then we ask, how will we install it? Or rather, how will we secure it after we put it in? And it's going to need some kind of hardware or fastener or clamping. How do I maintain this flush against that wall so that makes contact and we don't have movement in this direction? So that's answered first by an E-clip. This is fairly standard in some automotive applications. And they're ubiquitous, long-standing parts that's found in several trades, found all around, low cost. And so I grabbed one of these to try it out. Now, how will we mate with the E-clip? How will we make sure that this thing accepts this E-clip? That is going to be a matter of, these are designated for a certain diameter, like it's essentially the diameter you'd measure around here, plus or minus some range. And so we take that information about this diameter and that gets plugged into this groove. So we have mating, let's zoom in. We have mating with the wall, then we have flush with the interior wall, and then we have a diameter here, and that is an answer to the question of what diameter will fit with the E-clip. Retaining ring, or C-clip sometimes they're called. And then how wide of a groove do we need to accept this E-clip? Well, then that's also defined by the E-clip geometry, and it's relating to the thickness of that E-clip. So we make a groove equal to that thickness, and then you can see it's sort of, it seems a little bit larger, but it's tapered. And that is a question of, how will my 3D printed model allow 3D printing without supports? Well, then we're not going to have overhangs. That's the answer to that question. And so that transforms, we add this chamfer here, that's going to eliminate that horizontal overhang. So that makes it easier to 3D print. So you can start to see that each one of the design questions can be enumerated and they can be matched to a feature. If you're designing systematically, then they can be matched to a feature or a dimension inside your CAD model. Once we got that far, then you would have this bolt or shaft pass in, and it would probably start to wobble because we have a slip fit here. And so you have some play that's going to be allowed unless these are drilled. Post-processing, we want to eliminate post-processing. So keeping that, how can we keep it from tilting this far and this far? Well, then we're going to add a thickness on this side. So prior to this design question, we didn't have all this thickness. We just had a millimeter or so here. That would allow it's less support on the shaft. So you can imagine now we're contacting the shaft in a range, let's say as wide as my finger. And this is a ballpark choice of 10 or 12 millimeters. And it is simply large enough to control the alignment of the shaft in general. And then controlling more carefully will be the job of having 2 of these that will increase the constraint from this narrow range to all the way out here. That elongating that constrained circular region gives us a more careful alignment of this shaft being perpendicular to, say, parallel to the floor where this is set down. All of the questions so far that are answered in that design that we discussed are general design questions. And that I mean that these answers can be borrowed from other parts. They can be taken from my design rules because I'm using those answers all of the time. For instance, what is the size of the clearance fit? Well, we took an 8mm shaft. Then we always add 0.6. I always add 0.6 millimeters to that design for 3D printing, and in the case of we're printing in this direction. So 0.6 is the closing, the overbuild. It's related to overbuild, and I'll talk about that another time. Then you have the questions that are a little bit more detailed, such as if you place this in here, and then we're using this retaining ring, which is designed usually for contacting metals. It has a really strong pinching force, this force in this direction, and it has that force concentrated on these narrow regions when it's being inserted. So then the question is this metal, is it going to be too much force? Or if I install this 2 times and remove it, is it going to damage that printed plastic? And if I'm just printing with ordinary settings, then I have a hollow region. Actually, this is 30% infill on this part. Am I going to have a fight between my printer settings and the survival of this plastic? That is something that we can't really compute. It would be unreasonable to try to put that into an FEA simulation or something when you could instead just print the part and do some verification. So we're going to specifically observe, this is my activity, specifically observe pushing this on. The answer to that question was interesting. I was able to install this multiple times. The installation goes with some pliers. You'll need a tool because it's really hard to push that with your fingers. And well, I don't know if I can demonstrate right on camera, but okay. So it goes on pretty neat. And when I remove that, you will find a little bit of superficial damage on the plastic. It looks like it's not changing the net shape, but the plastic is surviving good enough we could get by. However, installing and uninstalling multiple times leads me to discover that that's just difficult. And if you use a tool, you're going to have to be very careful not to jab your fingers or something like that. And so I've modified the C-clip in this case. Oof. So this C-clip is the exact same part as this, but it has been reduced in the spring force it takes to close it. The net interior diameter has no change, but we've reduced the spring force by reducing the thickness of that spring region, just by grinding it out with basically a Dremel and some carbide. You could equally do that with a file. And so that was the answer to the research question of how does it work out trying to install these on plastic. And it's a little bit easier to handle it with your fingers and just get a sense of the force that it's going to take to install it, etc. So now we have a brand new option. We have the option of if your off-the-shelf part fits nicely, you can do that. But if you want to be able to turn it and adjust it, let's say this edge is going to interfere with the interior corner of the wall. So you've got to install it this way, etc. You get more control by taking a moment to grind these, or you could grind down the corners, etc. It can go further and further, the discovery of options that you have. But the simplest option is described simply. I can measure this and say, prescribe this for the design and say it's going to have a C-clip, and you're going to have only a 2mm spring arms on it. And so I would consider that type of question that requires some exploration and data gathering the research design questions. But once these are done, once we've accumulated these, and I've accumulated a lot so far, we then have new options that we can just copy and paste in other designs. And since these are extremely popular, and 3D printing with ABS is very popular, if I include this data, other people can reuse that solution in many other situations. It's just a matter of how many research questions, which questions am I answering in my documentation, and how do I describe that sufficiently to get transfer the understanding to the audience. That moves it down from a research question into a design question. The next person can just say, how do I retain the thing? Well, I can use an E-clip that's been reduced in its spring force. Okay, so all of this design discussion only matters if the assembly can actually bear a load, which it can. So I'll show you jumping ahead and running a test on one of these parts. Just understand there's a few variations. You'll see the one that has the bearing, and all these variations have the same geometry in common, which bears the load. So we make a press fit of the bearing into the part, and then we install it. And what we're going to have is when the shaft pushes down on the bearing, it's going to want to tilt like this. It's going to be pulling on some of the features because there's a moment on the part. Only if the bearing was centered directly over that wall could we have no tilting or twisting and no moment. So given that constraint, that limitation, how much weight can we hold? So far I've tested only using this method. So I set a block on top of those shafts. I keep it from slipping out of place with those pieces of cork, and then we can start pressing on it. And to press more, I can come over here, set the wood on it. I'm going to steady my hands on this bench, but I'm going to put my weight on the assembly. Okay, so I can stand on there. Oh, I just tilted back to my heel. I'm sure that I just put all of my weight on there. And so we have no problems, no defect from performing these tests. So that, even if we don't use it in that heavy of a range, we have a really good starting point to know what applications, what span of loads can we tolerate on an assembly like this. Okay, now I'm going to voice over a little bit and improve this explanation. I took a moment to carefully define design because we have a more complicated situation than a typical design. We're creating a parametric part, and then that part is developing sister parts or children parts that have some similarities and some differences. The first 5 questions that I wrote in black are considered to be the questions answered for this initial design. The bushing style part, which has no bearings and it has the simplest geometry. Each of the numbered items, such as number 1, it says hold steady. That is corresponding to a question. How will we hold the shaft steady? And we mentioned the answer. It's going to have a slit fit, but it'll sit resting on the interior hull of the part. And so each of these questions, well, these answers aren't written down in words anywhere. They are built into the geometry of that physical part. And they are stored, for instance, in the CAD model. They get carried over to the physical part that gets printed. So when I publish this design and call it sleeve, that's sleeve.solid part. That's a design that takes all questions 1 through 5 and delivers an answer. And then to demonstrate adding on another criteria to the same set of answers, as intended from the very start. We have the same design where most of the features are in common because those features answer these questions. So sleeve BR is for a sleeve with a bearing, and it simply has a widened shell, and now it carries this bearing for an 8mm shaft. It's a 608 bearing. And so if you want 1 through 6, those are in the file called sleeve BR, but the file starts to get more complicated. So this is where my methods break off from traditional engineering design methods. We have a second part, which you could consider a version 2, that enhances the design for one specific application, but not for every application. So I want to take this group of features, all in the CAD model, where we have answered a cohesive set of questions before proceeding, and save this and give it a name, and then describe in documentation what is the function of that specific part, so other users can download and access and reuse the solutions that are already embedded in the part, and then proceed to make a second version and give it a name. So here are these 3 parts side by side. Sleeve, which was made first, sleeve BR that was derived from this one, and BR inch, which was derived from this one. And each time I made changes to add value, right? But some of those changes remove value that lives inside of this one. So for example, if you want an assembly that's low cost and minimal, you don't need this ultra low friction, then you wouldn't want to spend the money on these bearings. And so each one of them deserves to exist. That's why I'm publishing multiple solid files instead of just one. I'll add a personal note here that can only come from experience. Okay, so you have this open source robot. It has 100 very useful, very versatile components. It was specifically designed so that the modules inside would have their own value in student projects. That's all related to my role as an educator at the university. But inside that design, nobody is actually discovering the parts and the components and the value of those parts. So I've published this robot that we're talking years ago. Let's say you get 100 downloads on GrabCAD and truly any other platform. No one's expecting that we're designing in this way to actually help them. So I'll publish this, get 100 downloads, and then separately later, I'm like, there's so much more in here. I'll publish the design of this little fan or this little terminal. And that design will get 5,000 downloads in a month. And it's just showing, it's because no one is expecting that the assembly and the parts inside of a large design are made up to the quality that those components are actually helpful to them. And that makes sense. It's not an ordinary thing. We don't put the details usually into all of our parts in such a manner that this bracket here, this design that I publish on the robot, is more useful to you than getting this design from the manufacturer, because I cleaned up the model and made it easier to work with and added names and datums and everything that the engineers need to proceed from there. And so many interactions like that have led me to, let's say if I publish a part, I've got to focus on the part. And so I'll still create assemblies and demonstrations, but I'm going to focus the communication and explain that the value in this part is so much more. And you're looking at a part that's far more refined, where the effort went into this and not into this. The refined effort is in here, and so let's publish the parts individually and describe them. And that has formed my mindset about how I'm publishing open source models, and it is unlocking this awareness that, okay, these models aren't all equivalent. You can design specifically for open source, and it's a lot more helpful for the recipient, for the downloader. And then People have had their goodwill, and actually they're raising their quality together, and we're learning from each other. Okay, we have a design, we have a sleeve. Now, if we install 2 of these, we support a shaft. If we install 2 more, we could have 2 shafts. Maybe that's the simplest application we can go to. But we covered design questions and the need. Now, one of those needs can fit in an application, and that looks like this. We have a gearbox or a belt box, not sure. Anyway, we can use a chain, or we could use any other driving mechanism, such as a belt, or even a simple O-ring made to be used as a belt. In this case, we have a 25-tooth pulley on the input shaft and an output shaft with 10 teeth. So it's a 2.5 times increase if we're driving the system from this side. So if I drive it with my driver, it spins. We have everything moving. And this can handle a fair amount of torque. There hasn't been much testing yet. But in any case, that works. And so we could continue with that example. What might I get? What would I want that for? One example is a high-speed tool, just like a Dremel, only having more torque, which is something that I very much need. We could make this to be mounted on a bench top, and that's something I actually want, a bench top mounted driving tool to drive these tools that have a 1/8 inch shaft or 3.2 millimeter shaft, like this carbide burr, because when you have this high speed, it's a whole different range of utility compared with the lower speed tools. Almost everything in our shops are somewhere around 3,000 and less RPMs, whereas this one goes up to 25,000 RPMs. And it really changes the functionality. It changes which devices you'd want to connect with it. And so I'd like to work towards that, and maybe many other people will work towards their own applications or the same, and that can be a collaborative thing. But at least now we have one demonstration that we can make our initial observations and start to test and examine what's possible and what would need to be adjusted. The next application demonstrates meeting a completely different outcome with mostly the same needs. And so this same sleeve is being used. And this is a variation of the model, mostly with shared features and then the added bearing. And this is the bearing that has a 1/2 inch inner diameter. And so this part is 90% of the work was already done in the initial design. We add a very small effort to accommodate that bearing, and then we can do a completely different thing. I'm not really intending to use this assembly. I wanted to tinker, and I wanted to explore, well, how much load can we put in this steel box, and how much will things fall apart if we start to spin it? And so that is a significant amount of mass, and that's just giving me more data that I can use to decide on what configurations, what are the limitations of the parts directly 3D printed as they are. And well, this whole situation starts with observations. I don't have too much to say about it because this was a quick project just for me to play. You can see I screwed these into the 2x4 just to get something mounted and to be able to get this lathe chuck spinning. This is around $60 on Amazon, and so now we are seeing this printegration. Integrating these off-the-shelf parts gives us easy access to start configuring a machine however you want to. If you want to configure the drive, the driving input, spinning shaft the way that you want to, and the speed that you want to. Now we're starting to get that freedom. So we basically have these three parts forming a tree where the most of the work and most of the trouble to find answers and test things out was performed on this main branch, that sleeve solid part. These ones are derived. Okay, now why do I not just make three configurations of one file? Why am I publishing three files? That's where we come and we find that there's been branched off already this sleeve variation where we have the offset and the centered version. Those already come from inside of sleeve. And so you have sleeve OFS for offset. That's the one that has the 3 millimeters moved over center line. Okay, but the sleeve OFS, this is a configuration inside of sleeve, and it's defined by having this, this dimension here where we have our offset distance. And so that's offset. That's a variable that lives inside the CAD model. And any designer can open up the file and adjust that. And so we have not just different configurations with this parameter, but a whole range that you can make this 0, or you can make it, maybe you can go all the way up to 5 millimeters. And you can place that anywhere that you need to. And if I were designing the next assembly, let's say I'm going to use this rubber belt and I want an exact offset, then I'm going to choose a new value for this. And I'm going to then produce the, let's say, the STL model and then print. And this may be saved inside of a folder that has all the other parts for my belt-driven assembly. So if this is one parameter, and that's the offset. There are a couple of other parameters as well. So for example, this whole, this series of humps that's intended to mate with this is called a 1/2-inch trade size. The hole in this box, it's because it goes with the 1/2-inch trade. It's much larger than a 1/2 inch, 22-ish millimeters. That goes with the EMT conduit, that's 1/2 inch. And we have 3/4 inch. And we also have unlimited numbers of holes in every other thin-walled steel or metal apparatus. You may want to change the thickness of this region here for a different thickness of a wall. This part still has enough engineering in it that it's worth it to copy the part or copy those features rather than reproducing all of the exploration that it takes. We know that it works. We know how much gap you need between the dimension of this and the dimension of a hole. And so you can retain that, reproduce, you can make several adjustments of variables, and then reproduce that design very, very quickly. So how does all that look in the CAD model? Well, we come from the feature tree, that's the default tab, over to Configuration Manager. And if you were to just open this and start working with it, you'll see these two configurations. It's a double click to go to the offset configuration or to go back to this one. And when you go into those, oops, hey, stop that. You can see this cut rectangle, for example. It is simply suppressed. So the feature is added. The information is still in this file, but it is not manifesting itself. And that's exactly the same as commenting out our code. Okay, from this point, I think I'll do a voiceover to abbreviate this section I had recorded because we're kind of going into the details of how this functions inside the CAD model, but that's all depending on somebody who's using SolidWorks. However, the workflows are similar in all of the other CAD programs. It's just a question of whether the designer actually implemented more layers of detail in a CAD model or not. And so that discussion of how to handle these details on the possible variations of parts and still maintain the functionality and somehow potentially make these designs and their options more available to users way outside of mechanical engineering or outside of the expertise with SolidWorks. That's what we want to go for ultimately. And so for details on files, I will maybe put this together in a different video. Hopefully you get a sense from this video altogether that we're extremely close to a world where tons of mechanical things can be simply downloaded for free and printed by people that are not engineers, but simply have some hands-on interest in building things. So for me, this is one part out of a series that will go, first of all, to my students that are engineering undergrads, and then they have access to, if they're doing an electronics project, they have some template parts on mechanical projects that they can equip themselves on the discipline that they're not experts in. It's something that we should have had from the beginning. If you were to open up a mechanical engineering textbook like this Shigley's Mechanical Engineering Design, I've got these little bookmark tabs wherever a major section is listed, and it doesn't actually take all that many parametric parts to cover the 90% range of mechanical things that we would want. It can all be really easy if we follow a few rules, which is design for 3D printing, design to integrate the most important off-the-shelf parts, and design open source in a way that leaves it accessible when we get to that stage where online we figure out how to really distribute and make these available and understandable in the way that we want to for everybody.